All right, people, get comfortable. Get comfortable because we're going to work on the entire semester review. Now, this will be posted online so you could print your own if you'd like and maybe see some of the stuff a little bit better. And there's 86 questions on here, but I'm not going to ask you all 86, but I'm going to go over everything. So here you go. If you can dodge a wrench, you can dodge a ball. All right, here's a card of sodium from the periodic table. How many protons, neutrons, and electrons? Okay, first, how many protons? 11. That is the number of protons, the number on top. How many neutrons? You would take the atomic mass and you would say 23 minus 11 equals 12. How many electrons? Well, if we're assuming this is neutral, if there's 11 protons, there's also going to be 11 electrons. If there's 11 pluses, why do I keep making an 8? 11 pluses, there's going to be 11 negatives. Draw a Bohr model of sodium. 2, 1, 2, 3, 4, 5, 6, 7, 8, and 1. So we'd write 2, 8, 1. How did you do that, Mr. Perkins? Well, let's look at this little periodic table. Sodium is right here. It's that dot. So we're going like this. How many are in the first ring? How many squares would we go by? 2. Then in the second row down, we would go by 8 squares, 8. And then we'd stop at 1. So 2, 8, 1. Write an Aufbau sequence for sodium. Okay. The two columns over here are the S's. These are the P's. And these 10 in the middle are the D's, okay? So for sodium, we're going to go first, 1. Here are the periods, 1, 2, 3, 4, 5, 6, 7. I know this is small, but look at it hard. If we're going to get the sodium, we're going to go by these two, 1s2. And then we're going to go down the second period. How many are there? 8. Excuse me. Right here, we're in 2s2. Then these are the p's, 2p6. Then we get to here, 3s1. Now, there's all kinds of Edpuzzles and stuff on this. If that's not enough for you, go back and look at it. Which letter represents the position 2p5? Right there, A. List 2 letters which would have the same number of energy levels in a Bohr model. That means list 2 that would have the same number of circles. Well, C, B, and A would all have 2 circles if you drew a Bohr model of them, okay? Which letter would represent an atom with the highest number of valence electrons? Well, out of these, it would be A, because A would have 7. Now, the actual highest number of valence electrons you could get is 8, and that would come from this column right here, right? Which 2 letters have the same number of valence electrons? Both of these guys right here, C and D, they both have 1 valence electron because they're in the same column. Let's keep rolling. This is fun, isn't it? Yes, that's sarcasm. I'm sure you're not having a great time. All right, here we've got a little graph. This is our graph. This is our melting our ice, okay? Why is the graph flat from 0 to 6 minutes? Because the ice is melting and the temperature can't go up. The ice is melting, all right? After 15 minutes, what would you see in the beaker right there? You're just going to see a liquid. You can tell it's just a liquid because the temperature is shooting up right here at this point. All right? Right here is your melting. Right here you got a pure liquid, the temperature's shooting up. Right here you got boiling. Where on the graph could you find both water and gas in the beaker? Right here, this area. That whole area right there. So like, I don't know, 20 to 25 minutes, something like that. Is this fresh water? Yes. And you can tell it is because it's down here, the freezing is at 0 and the boiling is at 100. So this is a graph of fresh water. List the deadly 7, okay? they're going to be hydrogen, then nitrogen, oxygen, fluorine, and then we're going to go down the halogens, chlorine, bromine, iodine. 1, 2, 3, 4, 5, 6, 7. Name the molecular shapes for each. This is bent. This one, if you can see, the middle is higher. That's trigonal pyramidal. This has got 4 outer ones, making 4 triangles. That's tetrahedral. And this one is linear. All right? Which is more strongly bonded, O2 or N2? Okay, that's going to be N2. O2 is double bonded. N2 is triple bonded. Of the above molecular shapes, which two are nonpolar? Which two are all the sides the same on? And that's going to be this one and this one, 15 and 16. These two have tops and bottoms. These two, there's no top or bottom to those. All right, now we're looking at some naming rules. LICL. Okay, let's draw a little picture of the chart over here. I know this doesn't look just right, but just bear with me, okay? All right, so here's the stairs. LICL crosses the stairs from the tall rows over here. So you just add lithium chloride. MgCl2, guess what? Boop, same thing. Magnesium chloride. SF6, ooh, the S and the F are both from over here. So they're going to be rule number 3, which means we have to use the numerical prefixes. This is sulfur hexafluoride. Okay. And SCO, ooh, scandium is right here. Now we're crossing the road from the middle. We do not know the oxidation numbers of the guys in the middle. If we look, if there's one scandium and it's bonded to an oxygen, we know the oxygen's -2. So this scandium has to be +2. Scandium 2 oxide. Down here, N2O, they both come from over here. That's going to be rule number 3. Dinitrogen. Lord, what's wrong with me? Dinitrogen monoxide. So that's rule number 3. That's rule number 2. Rule number 3. Rule number 1. Rule number 1. How's that? Feeling that? Balance and label these. Okay, This is obviously the Haber process, right? That plus that equals one thing. That's synthesis. Okay. This is going to be 1, 3, 2. All right. This one right here. Got 3 oxygens. I've got 2 right there. So we need a 3 and a 2 to bring them both up to 6. 2, 2, 3. And 26. Sodium and soda. Ooh, we need a 2 for the fluorine, right? 2 Fs. That gives me 2 NAs. Boom. I've got 2 Cls here already. 2, 1, 2, 1. Let's go back and label this one. That one's falling apart. It's a decomposition. And this one guy, this girl replaces that girl. Single replacement. Again, if some of this stuff doesn't seem familiar to you, go back and look at the ed puzzles. Go back and look at anything. Everything is digital. Everything is on your computer. You can't say, oh, I don't remember how to do this, and walk away. Go back and look at it. Everything is at your fingertips, okay? I know for a fact that your teacher, your chemistry teacher, I know him well. He worked really hard to make sure you would have all this information at your fingertips. He's also a very handsome and smart person. Balance and circle the precipitate. Okay, we got to balance this bad boy. See what the balance is. I'm gonna two NAs. I'm gonna put a 2 there. Gives me 2 CLs. All right, a carbonate. 1121 sounds good. Circle the precipitate. Okay, here's what we have to do. We see the two things that are being produced are sodium chloride and calcium carbonate. So we look on the top of page 6 and we see that all carbonates, with no exceptions, except group one, all carbonates, and calcium is not group 1, so all carbonates are insoluble. So that's the precipitate, all right? Balance this one. 3, let's see, I'll put a 3 there. 3, 1, 3, 1, and circle the precipitate. All right, these are chlorides. All the chlorides are soluble. Hydroxide. All hydroxides are insoluble except group 1. Is aluminum a group 1? No. Brap. There you go. Those are our precipitates. Precipitates are insoluble. Okay, let's keep rolling here. Give the number of moles, 30 grams of phosphoric acid. 30 grams. 1 mole would weigh, let's see, that's 3 plus 31 plus 64. That's going to be 95. That's 98 grams. 30 out of 98. 30 divided by 98. 0.31 moles. Okay, and if you're like, Mr. Perkins, you're going too fast, well, rewind it. Watch it again, okay? You can do this. All right, give the following number of moles. 1.5 times 10 to the 23rd compounds. Okay, we have 1.5 times 10 to the 23rd, but there are 6.02 times 10 to the 23rd per mole. So that percentage, 0.5 EE23 divided by 6.02 EE23 equals 0.25 moles. 0.25 moles. See? And then 100 liters of carbon dioxide. How many liters are in a mole of gas at STP? That's right, 22.4. So you have 110 liters. 22.4 liters is a mole, so you're going to have more than a mole. 110 divided by 24 equals 4.58 moles. Or 4.6, however we're going to round it. We've been rounding a lot, but that's fine. All right. Solve the following. 30 liters of oxygen has a mass of blank grams. Now, this is a 2-step problem or a 3-step problem, depending on how you're thinking about it. 30 liters. Let's figure out how many moles that is. 30 liters out of 22.4 liters. That's going to give us 30 divided by 22.4 equals, it's going to give us 1.34 moles. Okay? And it's O2. O2 weighs 32 grams per mole, right? You look at the chart, oxygen 16, O2 weighs 32. So you have 1.34 times 32 grams per mole, 42.9 grams. Let's try the next one. Now, this is the V-shaped equation. That's how you see me work it. You can go back and definitely watch me work these problems in another way, no problem. 2.6 times 10 to the 23rd atoms of magnesium have a mass of blank grams. Okay, I'll write this one in the V shape. 2.6 times 10 to the 23rd over 1 times 1 over 6.02 times 10 to the 23rd times magnesium, 24 grams over 1 for magnesium. This is the same problem. I'm just showing you the V, the way we do it in the V here, okay? So we'll say 2.6 EE23 divided by 6.02 EE23 times 24. 10.4 grams. All right. And then let's take a look down here at the bottom. You can work this one. 5.9 times 10 to the 24th molecules of NO2 would fill a balloon to how many liters? 5.9 times 10 to the 24th over 1 times 1 over the proper number, 6.02, times 10 to the 23rd, times, we're looking for liters. What's the proper number for liters? 22.4 liters per mole at STP. So here we go. 5.9 times 10 to the 23rd divided by 6.02 times 10 to the 23rd times 22. My calculator's off. Nice. 0.9 EE23 divided by 6.02 EE23 times 22.4 equals 21.95, or we'll just call it 22 liters. We'll just round that one off. Okay, excellent. Let's keep going. We're almost halfway through this bad boy. All right. Percent composition. Give the percent of each element in the following compounds. All right, Na2O. Na is 23, so we got 23 plus 23 plus 16. So that's going to be 46 plus 16, that's 62 grams. The sodium is 46 of those grams. So the sodium, 46 out of the 62 is sodium. That's 0.74 or 74% sodium. Then the rest has got to be oxygen, so we'll just say 26% oxygen, right? Because the percentages have to add up to 100. Here we have copper 1 nitrate. All right, copper, we round that off to 64. Nitrogen 14. 3 oxygens is going to be 48. Let's add this up. That's, let's see, that's 62 plus 64. That's 126 grams. 64 out of the 126 is copper. 14 out of the 126 is nitrogen. And 48 out of the 126 is oxygen. Does that make sense? We can do this. 64 out of 126. That's equal to, we'll call that 51%. 51% copper. 14 out of the 126. 11% nitrogen. And 48 out of the 126 is 38% oxygen. So there's our percentages. All right. Keep rolling. Now we've got some stoichiometry here. This section is stoichiometry. All right. Here we go. It's balanced 4, 1, 2. If 3 moles of lithium is heated with excess oxygen, how many moles of lithium oxide will be produced? So 4 is the number here, so you say 3 out of 4, all right? Instead of the 4, we're going to put a 3 there, 3 moles of lithium. So 3 instead of 4 would be equal to how many moles of lithium oxide? Here's lithium oxide. How many moles of lithium oxide? So 3 out of 4 equals X over 2. You cross multiply that, you get 1.5. 1.5 moles. Number 41. If 50 grams of lithium oxide was produced, so if you made 50 grams of this, okay, let's figure out how many moles that is first. 50 grams, and lithium oxide is 7 plus 7 plus 16, so that's 30. So that's going to be 1.67 moles, right? So in other words, if we had a 1.67 here instead of a 2, so we're going to say 1.67 over 2. Now let's see what else we're asked for. How many liters of oxygen gas were used? Here's oxygen, X over 1. X over 1 equals 1.67 over 2. So that's simple enough. 1.67 divided by 2 gives us 0.835 moles. And it says how many liters is that? How many moles, how many liters are there in a mole at STP? You're right, 22.4. So that's going to be that answer times 22.4 times 22.4. 18.7 liters. And here we go. 1.5 moles of lithium react, so 1.5 is to 4. How many grams of lithium oxide were produced? 1.5 is to 4 as X is to 2. So that's going to cross multiply 0.75 moles. But it says how many grams times lithium oxide, remember we said weighs 30 grams. So 0.75 out of 30. 22.5 grams. All right, again, replay it if you're not understanding. All right, and boom, now we're on the gas laws. Carbon dioxide occupies this volume container at STP. Okay, so we've got another pressure and a temperature here. What will be the volume? Ooh, there's a volume too. Now we know that we're going to have to use this formula. This problem is the combined gas law. This is not a Pivnert formula, all right? So our first volume is 1970. So I'm going to write it over here for you. The first volume is 1,970. And the first pressure is standard. First pressure and temperature are standard. So the standard temperature is 273 Kelvin. We have to use Kelvin. And since we're asking in kilopascals, for our first pressure, we're going to have to put 101.3 because that's the standard pressure for kilopascals. You're right. You can just look up the standard pressure for kilopascals right here on page 1. Okay, and that's going to be equal to, okay, we're going to change the volume. We don't know what the new volume is, but we know the new pressure is 170, and the new temperature is 26 Celsius. So that means we've got to add 26 to 273, 299 Kelvin. So we're solving for V2. We're going to cross multiply. 299 times 193 times 1970 divided by, let's get rid of this 170 here, 170 times 273. So those are the numbers that go on the bottom. Don't forget this parentheses, okay? I'm going to math it up right here for you. 299 times 101.3 times 1970 equals, divided by parentheses, 170 times 273, close those parentheses, equals 1285.7. 1286 milliliters, we'll call it. That's the new volume. Number 44. Oxygen occupies a fixed container of 6.5 liters at STP. What will be the new pressure if the temperature rises to 290? So oxygen is in a fixed container, so we don't have to use volume. This is just going to be pressure over temperature equals the new pressure over the new temperature. Okay, this is just Boyle's law. Gay-Lussac's law. Okay. So the volume doesn't matter. At STP, so at standard temperature and pressure, you'd say, and it says it's used millimeters of mercury. So standard pressure is 760 millimeters of mercury, and standard temperature is 273. So if we heat it up to 290, what's the new pressure? Cross multiply it. 290 times 760 divided by 273. Going to go up by a little bit. It's going to be 807.3 millimeters of mercury. All right, excellent. We're rolling now, people. We are rolling. We're rolling. Tell you what, I'm going to tell you right now, we're halfway through the semester. So we're going to break this video off and we're just going to make it a two-parter. So you have finished part 1 of the review. All right? And who knows, maybe part 2 will be easier because that stuff is fresh on your mind, right? So halfway through part 1. Did this help you? Check yes. Check yes, this did help me. No would be the wrong answer.